Hello students. So in the last class you saw how electrostatic charges can be produced, their properties, and of course the Coulomb's law. Now today in this particular class you are going to learn one very important topic in this particular chapter, and that is called electric potential at a point. Now let this be a charged body and let it be positively charged. Why positive? Because we have to think positive and be positive. Now around the charged body at any point you find the electric potential. So let us assume that this is a point A where we need to find out its potential, and of course the meaning of the potential at a point A. Okay, now in order to explain the concept of potential, we have to take a unit positive charge. Okay, unit positive charge. Okay, not very close to A, okay, but at infinity. Although we can't show infinity on the board, so let's, for our convenience, let that point, okay, the point at infinity be at this point. Okay, so this is the point at infinity, and at this point we have to assume a unit positive charge. So in order to bring this unit positive charge from infinity to the point A, we have to apply some force, isn't it? And there is a displacement also, isn't it? And whenever there is force and displacement, okay, the product of these two will give you the work. So you see, some work is done in order to bring a unit positive charge which is present at infinity, okay, to the point A. So that work done is known as the potential at A. Okay, hence potential at a point is defined as the work done in bringing a unit positive charge from infinity to that point. So this is the concept of the potential or the electric potential at a point, and you have to know its SI unit also. The SI unit of electric potential at a point is volt, and it is denoted by V. Okay, and then the same explanation, okay, will help you to understand the meaning of volt. So what is 1 volt? So the potential at a point, let's say at the point A, is said to be 1 volt, okay, if 1 joule of work, okay, is done in carrying a unit charge. That means 1 coulomb charge from infinity to that point. So that is the meaning of volt. All right. Now with this, I want to show you another similar topic to you. Now let B be another point, okay, which is closer to the charged body. So what will be the potential at the point B? It's like A, isn't it? Potential at the point B means the total work done in carrying a unit positive charge from infinity to the point B. So in both the cases you are carrying 1 coulomb charge, isn't it? But at the point A, this much is the displacement, isn't it? When the charge is brought from infinity to the point B, you see the displacement is more out here, isn't it? Since the displacement is more, okay, the work done will be more, and hence the potential at the point B will be more than the potential at the point A. So What do you understand from this? As we move closer and closer to a charged body, the potential increases, and as we move away, the potential decreases. All right. Now, just to understand, okay, let's give the potential some values. Let's say the potential here is 20 volt and the potential here is 18 volt. So you see there is a difference between these two, no? So what is the difference of potential between B and A? This is 20 minus 18, that is 2 volt. And what is that 2 volt equal to? It is 20 minus 18, no? So when you subtract this much from this much, you get this 2 volt, isn't it? That's why we say this is the difference in potential, and it is called the potential difference. So potential difference between 2 points is the work done in carrying a unit positive charge from one point to another, not from infinity to A or infinity to B, from one point to another. That's why the next topic is potential difference. Now, potential difference between 2 points is what? It is the work done in bringing a unit positive charge from one point to another point, and it has the same unit as the potential at a point. So, its SI unit is also the same, that is volt. EMF, or the electromotive force of a cell, and by cell we mean an electric cell, not a biological cell. Okay, now before going on to this topic, let's understand about cell, that means electric cell. So what's an electric cell? An electric cell is a device that converts chemical energy into electrical energy. Okay, for instance, the cell which you use in a torch, okay, so that contains chemicals inside it, okay, and that produces the electric current. We have different kinds of cells which you can see out here also. Although they look different, but they all have few things common. Okay, they all have two electrodes, one positive and one negative electrode, and they all have one or a mixture of chemicals, and that's called electrolyte or exciting liquids. Okay, so for your convenience, I'm drawing a dry cell. So this is a dry cell. You know, this part is the positive of the cell, and this end acts as the negative electrode of the cell. Okay, so this is how a dry cell looks like. Okay, but in a circuit we represent an electric cell by two parallel and unequal lines, like this, longer line and a shorter line. Okay, the longer line represents the positive electrode of the cell, and the shorter one indicates the negative electrode. All right, so that's all about the electric cell and different types. No, you know, when there are 2 points in an electric field, there will be potential difference between the 2 points, isn't it? Similar kind of potential difference exists in between the two electrodes of the cell also. Okay, so that means this is the positive and this is the negative, isn't it? So this potential difference that exists in between the two electrodes of a cell, when the cell is not connected to an external circuit, that means when the cell is open circuited, okay, that potential difference between the two electrodes is known as the EMF, or the electromotive force of the cell. Now let's have some examples of the EMF. Okay, different cells have different EMF. For instance, a dry cell has a EMF of 1.5 volt, while a Daniel cell has EMF of 1.08 volt. In the diagram, PQ is a resistance that is connected to the two terminals of a dry cell. So as soon as we connect the resistance to the cell, electrons from the negative electrode will flow through the resistance and come back to the positive electrode, and there will be continuous flow of electrons. That means electrons through the resistance will be flowing from, you can see, from Q to P. No? So let's say Q amount of charge flows through the resistance in T seconds. Okay, so in T seconds, how many charges are flowing? Q. So in 1 second, how many charges will flow? So it's Q by T. So what is this? This is the amount of charges that will flow in 1 second. And isn't this the rate of flow of charge? Rate of flow of charge. This rate of flow of charge is known as. So electric current is defined as the rate of flow of electric charge. Alright, and the formula for this is, if I be the current, then it is the rate of flow of charge. Isn't this the rate of flow of charge? So it is Q by T. So this is the formula for electric current. Now let's see its direction also. Okay, now in the diagram you can see electrons are flowing from Q to P, isn't it? But by convention, okay, the direction of the positive charge, okay, is taken as the direction of electric current, not the negative charge. Okay, electrons are negatively charged, isn't it? So since negative charge, that means electrons are flowing from Q to P. So we can imagine that positive charges are flowing from P to Q, isn't it? That's why the direction of the current is from P to Q. Alright, so you can see from the diagram also, okay, that current always flows from the positive electrode to the negative electrode of a cell through the circuit. And now the SI unit of current is ampere, and let's see its definition also from the same formula, Q by T. If 1 coulomb of charge, okay, flows through a wire in 1 second, okay, the current flowing through the wire is said to be 1 ampere. So that's how we define ampere. It is, let's take few things which flow, okay, like any liquid heat also, it can flow, isn't it? Now for a liquid to flow, there must be difference of height, isn't it? Because a liquid flows from higher level to a lower level. Similarly, heat also flows from higher value of a physical quantity to a lower value of that physical quantity. What is that? That is temperature, from higher temperature to a lower temperature, isn't it? So heat flows like this from a point of higher temperature to lower temperature, and liquid flows from higher level to a lower level. Now think of electric current. Electric current, like a liquid or heat, electric current also flows, isn't it? And a flowing object, okay, flows from higher value to a lower value, isn't it? Similarly, electric current, suppose if this is a wire, these are the 2 points A and B. If A is at higher value of that physical quantity and B is at lower value, what should this physical quantity be? It is potential. So electric current flows from higher potential to lower potential. All right. Now let's remove heat and let's concentrate on liquid and current only. Now when this much is the inclination and this much is the difference in height, so you can see this is the difference in height, isn't it, of these 2 points. So when this much is the difference in height, liquid will flow with some speed. No? Now what will happen if I increase the difference of level? Initially this much was the difference in level, and now you see this much is the difference in level. You can see the difference has increased, isn't it? Now how will the liquid flow on this surface? It will flow much faster, isn't it? That means the rate of flow of liquid will increase. Okay, so as the difference of height increases, then the rate of flow of the liquid will also increase. Now similar kind of thing happens in case of electric current also. So this is the wire, these two are the 2 points as usual. Let's say A is at a potential 20 volt and B has a potential 18 volt. Okay, so since there is a potential difference, current will flow from higher potential to lower potential. That's why current I flows from A to B. Okay, now what is the difference of potential, or the potential difference here? 20 minus 18 is 2 volt. Now let's see what happens when we increase the potential difference. Okay, now for that what I am doing is I am keeping the point B at the same potential 18 and I am increasing the potential of this to, let's say, 25 volt. So what is the potential difference right now? This means this is 7 volt. So it has increased, no? What has increased? The potential difference has increased. Okay, so as the potential difference increases, the rate of flow should also increase, isn't it? What is actually flowing? The charges are flowing, isn't it? So as we increase the potential difference, the rate of flow of charge will increase. The charges will flow faster and faster, isn't it? And what is that rate of flow of charges called? Current. So what does it mean? As we increase the potential difference, current will also increase, and as we decrease the potential difference, okay, current will also decrease. So that is actually given by the law, which is one of the most important law in this particular chapter, and this is known as Ohm's law. The law states that temperature and other physical conditions remaining the same, the electric current flowing through a conductor is directly proportional to the potential difference between its ends. So, It means the same thing, isn't it? That means as we increase the potential difference, current will also increase, and as we decrease the potential difference, current will also decrease. Now let VA be the potential at A and VB be the potential at B. So the potential here is VA and the potential here is VB. Like in the previous case, it was 18, 20 and 18, no? So how we found out the potential difference? By subtracting these two, isn't it? By finding the difference of these two potential. So which is greater? This is greater because current is flowing from A to B. So A is at higher potential. So what is the potential difference here? VA minus VB. And according to Ohm's law, this is directly proportional to the current. And when you subtract the potential of B from potential of A, we get another answer, isn't it? Like the difference of 20 and 18 is 2, no? So 20 minus 18 is 2. This is the potential difference. Similarly, V is the potential difference. VA is not the potential difference. VV is not the potential difference, okay? This is the potential at A, this is the potential at B, and this is the potential difference. So this potential difference is directly proportional to I. And you know, it has to be replaced by is equal to an constant. And what is K here? K is the constant of proportionality, and this constant in this case is R, which is the resistance of the wire. That's why V equals to, this is R and I prefer to write like this, V is equal to IR. This is one of the most important formula of this particular chapter. V is the potential difference, I is the current, and R is the resistance. Now that is the x-axis, and this one is the y-axis. Now if we plot the values of current along y-axis and values of V, the potential difference, along x-axis, then we get a graph like this. That means a straight line passing through the origin, okay? So that oblique straight line means that as the value of the potential difference increases, the value of current will also increase. When the value of the potential difference is 0, the current will also become 0. So this is the characteristic feature of a conductor. Now the limitations of Ohm's law. Ohm's law is applicable only in case of ohmic resistances, okay? It's like the metals, for example, copper, silver, gold, aluminium, okay? These are the ohmic resistances, okay? So these ohmic resistances, okay, follow Ohm's law. But Ohm's law is not obeyed by non-ohmic resistances. Like the semiconductors or vacuum tubes. So these are the things which do not follow Ohm's law. Okay, so if that is so, then let's see the graph, okay, V versus I graph for the ohmic resistances, okay, and non-ohmic resistances. For ohmic resistances, V versus I graph will be an oblique straight line passing through the origin. For non-ohmic resistances, the graph will not be a straight line, okay? It will be a curved line somewhat like this. So as the graph goes up, it also means that as the value of potential difference increases, the current will also increase. In this case, the current is not directly proportional to V.